Good afternoon, everybody. Welcome to um, GYAN program on hyperbolic geometry, Riemann surfaces, and Teichmüller theory, which is for this week in School of Physical Sciences, JNU. This is a first mathematics program in JNU, and originally it was proposed in 2019 to be held in 2020, but as you know, in 2020 we had pandemic and it was postponed indefinitely. And we are very happy to have Professor Papadopoulos, Papadopoulos here with us as guest faculty who will be giving most of the lectures. Professor Papadopoulos is a Director of Research at the National Center for Scientific Research in Strasbourg, France, attached with Institute of Mathematical Research in Strasbourg. He is the author of more than 200 publications, and including 45 books. You can see his profile on his website, as well as you can see on MathSciNet. He spent 2 years at the Institute for Advanced Study, Princeton, USA, one of the most prestigious institute for mathematics in the world. And he taught at the University of Southern California, Brown University, at the City University of New York. He has also been to India several times, visiting TIFR Mumbai, ICTS Bangalore. He spent recently 6 weeks in Banaras Hindu University as a distinguished visiting professor, and he gave a course there. He's also visited Tsinghua University, Beijing, and University of Pisa, Florence, and others. And his main field of interest is geometry and topology. And he also has interest in history of mathematics, and he has published on history and philosophy of mathematics and on mathematics and music theory. We have a fine set of lecture by our renowned guest, Professor Papadopoulos, starting today, and all the lectures are between 2 and 5:30 on weekdays, and on Saturday it will be in the morning between 10 and 1. Our national coordinator from JNU for the GYAN program is Professor Satyabrat Patnaik, who has helped me all along. I was new to this, and he really, as you know, his office is next door to me, and I kept bugging him for every little thing and asking him. He was very helpful. And of course, our Dean School of Physical Sciences, Professor Shobin Sen, has given a lot of support and advice for this successful running of this program, and I'm sure it will go well. We have all these participants from various parts of India, and of course our School of Physical Sciences math students and some physics students. I welcome you all again, and now I would like to invite Professor Sobin Shen, our Dean, to speak a few words.
All right, so welcome you all to the School of Physical Sciences, JNU. And as you rightly been said by Riddhi, that this is after the first time after COVID, we have started again back this GYAN program, and we are very happy to also say, probably Satyabrat will talk about that we have now, I think, 12 GYAN program running in JNU itself. This year itself. So that's a fantastic thing that happened also with JNU, including 3 is typically coming to School of Physical Sciences. And this is the first in this series given by Professor Papadopoulos. And about the school, because obviously I'm representing the School of Physical Sciences, although it doesn't really say mathematical sciences, but this is the one of the best school that has all the 3 natural programs, that is physics, chemistry, and maths. And that's the reason you have also several people probably also coming from the physics background who are probably taking this course. In that way, so I think math started in School of Physical Sciences in 2009, I think the PhD programs, around 10, and master's started 2019. Similar time also chemistry was started, 7 and 17, but physics were there for a very, very long time. And that's the reason we're still with the School of Physical Sciences. And this way, it really works quite nice in many, many ways. We can actually have a cross-disciplinary interactions in many ways. We have here typically around 220 students, including masters and PhD. We only run the postgraduate master's degrees as well as PhD program in all the 3 subjects, physics, chemistry, and maths. And we have around, right now, around 38 faculty members distributed over 3 disciplines. So I think with this short introduction, I welcome you all for this a week-long program on this Gyan. As well as I welcome Professor Papadopoulos for coming and really visiting us, probably for the first time in JNU. We were just discussing that he visited ISI 1 or 2 times, but JNU next door, he's coming for the first time. So welcome to School of Physical Sciences for coming. In fact, we met long back before COVID time in Strasbourg when we were visiting over there. It's a very nice, this welcoming moment. It was there, in fact, when he first visited us over there. In fact, Satyabhat was also there at that time. With this, I really welcome you all, and please enjoy this, program. Thank you very much.
Thank you, Professor Shobhan Sen, for kind words. Now I would like to invite Professor Satyabhat Patnaik, the coordinator for the Gyan programs, to say a few words.
So, good afternoon, bon après-midi. We're very happy and glad that Professor Papadopoulos has kindly agreed to our request to be part of this Gyan JNU program. And of course, the maths program in JNU nucleated around 2007. It's a small program, but they're very high on aspiration. I mean, we really want to have a benchmark program. It's still in the process of nucleating a strong program. And Riddhi, of course, headed that program and has been there from the beginning. At the end of this 5-day course on hyperbolic geometry and deep Gyan on mathematics, if you want to remember something, please remember this is GIAN, not GYAN, Gyan. So this is Global Initiative of Academic Network, okay? So this is not really a set of lectures, a set of, conference talks, something like that. The idea of Gyan, which is entirely funded by Ministry of Education, is that you bring in the best in the field to Indian university campuses and institutes and expose our students and faculty to build up new networks. So we really want to smash the idea that people can download lectures from YouTube and can learn things. The guru is here and the shishyas are there. So this interaction, talking to one another, discussing, that's what we want to give the flavor. And this is the 52nd Gyan course in JNU, started in 2015. And it has its own plus and minus. In the days, I mean, the way we learn subjects, it has changed, particularly for students. Many of, I find that most of people just, through the internet, they probably get the best lectures or best focus on education. But here is an opportunity, the master is present, and you learn not just from the lectures, but also through interactions. I can take the liberty of saying that Professor is actually an Indophile. He comes to India quite frequently and he likes India to some extent. The brief interaction that we had in Strasbourg. Max Muller, who translated Upanishads and all this thing, never came to India. Apparently the idea was that I have such a high opinion about India that if I go there, expectations maybe may not stand true. So I hope that the mathematics that you would receive and that you would learn and they reciprocate, the expectation of our maths program and all that you're learning is proportionate to the amount of effort that professor would put in. With those few words, I welcome you all again. And remember, this is a GYAN program, G-I-A-N, not G-Y-A-N, of course you'll receive, but G-I-A-N, and entirely funded by Ministry of Education. It's a very new initiative, and this is not just for these 5 days. It should continue for many, many more months and years, more networking. Thank you very much.
Thank you, Professor Patnaik, for the introduction to GYAN programs and addressing the audience and welcoming Professor Papadopoulos. Now I would like to invite Professor Papadopoulos to speak a few words before he starts his lectures.
Thank you. Thank you very much for this introduction. I'm very glad to meet again 3 professors, which I met at various occasions. Some of the students I know already. As Professor Ridisha said, I come often to India, in fact, and I'm never disappointed. Each time it's when I leave, I'm a little bit sad of leaving because of the people I meet here. This is the main, the main thing I like. The open, interesting, and students willing to learn. And I talk about many things with my friends and colleagues here, and about Indian culture, Indian philosophy. I like the colors. I don't like the pollution very. This is the only thing which I don't like here. I don't know why. But the rest, I'm really very, very happy at each visit. I come almost every year, at least 1 or 2 this year. I will come 3 times, in fact, to all sorts of events. I'm also involved in history of mathematics, as Professor Shah said. So I come on a regular basis to conferences on history of mathematics. History of mathematics is not disjoint from mathematics, in fact, because history of mathematics for me means reading old texts by our masters, reading Euler's works, I will talk a little bit on hyperbolic geometry. So I started reading Lobachevsky, in fact, very interesting work. He wrote several books on hyperbolic geometry. This is the founder of hyperbolic geometry, and there are many things in his works that are not known. In fact, when people want to learn hyperbolic geometry, they just download a book, a modern book on hyperbolic geometry, and then you read what is inside and so on, theorem, proposition. But if you read the work of the founders, the works of the founders of hyperbolic geometry, there are amazing things which people are still not aware of. In fact, so this is just one example. I will talk a little bit about the geography, because it's related to what I will talk about, the geography, mainly the construction of geographical maps. What is the mathematics behind the construction of a geographical map? And I learned a lot by reading papers by Euler. He wrote several papers on geographical maps, which are amazing. In fact, there are many ideas inside that are still not exploited, in fact, by modern mathematicians. So this is my relation with the history of mathematics, and I have a best friend in Bombay, Professor S.G. Dani, who organized every year a conference on history of mathematics. So I went to several of his conferences. He has also a journal, Ganita Bharati, on history of mathematics. So he asked me to send him papers for this journal. So this is my relation with history of mathematics, which is related in several ways to my relation with India. And yes, I want to thank the organizer, Riddhi Shah, and the two professors who are in charge of this program, Gyan program. And I want you to learn, to have an idea a little bit of the mathematics I find interesting. This is I will talk about a topic on which I'm working since 40 years. So this is a long history of Teichmüller theory and maps between surfaces. Okay. Thank you.
Thank you, Professor Papadopoulos. We will start the program now. Please take this opportunity to learn from Professor Papadopoulos a new topic, but a lot of things you will find which are familiar to you, and it's if you try sincerely, I'm sure you will learn quite a lot. He's a very good expositor and speaker, and this is the unique opportunity for you to have him visit here and give you a set of lectures. So please learn, and you can ask questions to him mostly towards the end, but if you think something is very important, you can ask in between. And thank you, Professor Shen and Professor Patnaik. And we will start with the lectures in a couple of minutes. Thank you. Okay. So we need to remove the chairs. वो वाला नहीं, यही है. लाइट चलेगा? ये होगा.
There is. I put it in the other pocket.
Yeah. Can you remove the chairs?
You can keep the table. You can keep the table, but just the chairs. Just remove the chairs. You can keep the table. Thank you. I sent this picture here. Sorry, I sent this picture here. This is taken from an old book on biology, in fact, a very interesting book. A book which is rediscovered over and over again by scientists. In fact, it contains so many great ideas. I'll give you the reference. It's in the next slide. The book was written in 1917. I first heard about this book by reading an article by René Thom. Some of you might have heard of him. This is a mathematician from the late century, 20th century, a great French mathematician who got the Fields Medal, in fact, mainly on his work on topology. But he also worked on biology, and he invented this theory which you might have heard of, called catastrophe theory. it's I mean it's a great theory. So he writes several times in his even mathematical papers that all these ideas I got from reading this book by Darcy Thompson. So let me tell you why I find this interesting. In fact, recently there was also there's a lecture, in fact, by John Milner, who is also a Fields medalist, a great mathematician, and you can find the registration of the lectures on YouTube. He gave a lecture at the Institute for Advanced Study in Princeton about this book, in fact, by Darcy Thompson. I will give you the as I told you, in the next slide, the reference. And finally, also recently there was a biologist, a great biologist in France, who has had the chair of biology at Collège de France, which is the most prestigious. It's more than a university in France. It's a university, but there are no registered students. Everybody can come and hear the lectures, and I mean the greatest scientists are professors there. So his first lecture was precisely on this book by Darcy Thompson. So this is a map. This is supposed to suggest a map between this fish here and this fish here. The two fish are a priori very different. In fact, one of them, the size, this size is supposed, I mean, it's shown to be greater than this one, but in fact it's about 20 times greater in this is a very big fish, the one to the right. It lives in the Indian Ocean, and the shapes are very different. This map, what is suggesting is a natural map between the two fish. The suggestion, you see, it's these small rectangles here are sent to topological rectangles, but curved rectangles, and it suggests several things. In fact, first of all, the map preserves. You want to, so you see, people who work in biology, there are several trends. In fact, it's not like mathematics. In biology, you have several schools of several theories. So one of the theories, this is evolution theory. So the question is whether there was some evolution, continuous evolution from this fish to this one here. So you have this fish, you have this one here. So was there at some point in history some fish which is intermediate between the two? And how would it be? And how can we guess how it is? So this. So you want to have a family of maps, not only moving continuously from this fish to this fish, and you want the maps to I wrote it here, stratification preserving. So in the fish there are several strata. There are the wings, there are the eyes. You want the map to send the eye to the eye. You want it to send the mouse to the mouth. Of course, there may be there are other maps in terms of mathematics. There are other homeomorphisms between this fish and this fish, but you want in this biology theories, you want the maps for instance, to send this tail to this tail and so on. So this is called a stratification preserving homeomorphism. And by the way, René Thom, whom I mentioned, introduced the notion of stratification
stratified spaces in topology. And he writes, I learned the word stratification from this biology book. So this is just to tell you the importance of this map. So anyway, okay, as mathematicians, we do not, in principle, we do not care at all about biology or evolution or fish or anything like that. But we have a map from here, from this picture, in fact, to this picture. And a natural question is, okay, how can we measure the distortion of such a map? Of course, the map cannot preserve distances because, and even it cannot preserve distances up to scale because you see this distance is more or less the same as this, but the height here is very different from the height here. So the map cannot be a homotopy. It cannot preserve distances up to scale. So what is the question which a mathematician can ask? What is the best Lipschitz map between this between this figure to the left? This is one of the main topics which I will talk about. Best Lipschitz maps between surfaces. So now I want to go, yeah, okay, so this is also from the same book. Why did I get this? There's something below, maybe? Yeah, okay, thank you. Okay, thank you. So this is the title of the book. It's called On Growth and Form. It has been translated into French. I don't know what about Indian, but maybe someone from you, if you are interested, you can translate this book in Indian and publish it. I think it's a very important book. If there's no translation in Hindi, and since it's from 1917, there are no more any copyright. So, okay, so these are shells of crabs, and shells of different crabs. All of them have names. Usually the names are Latin names. They are written here, 2 small characters, but you don't need to read them. So all of them are crabs. And the same question, what is the best Lipschitz, mathematicians can ask, what is the best Lipschitz map from here to here? The map which has least distortion, least metrical distortion. And among all these, this could be, I mean, this is very natural mathematical question. I talked, how do I go? How do I go from page to page?
This one.
Okay, thank you. Okay, so I mentioned geography. I mentioned geography before, and you have the same question. In fact, the main question for geography, or the part of geography which is concerned with building geographical maps. I mentioned Euler, and this is also Euler's concern about geography. Is well, you have a country. In principle, the Earth is considered as a sphere. You have a country drawn on the sphere, and you want to represent it on a piece of paper which is Euclidean. It has Euclidean geometry. A piece from spherical geometry to a piece of Euclidean geometry. What is the best way you can represent it? And the best way is the way which distorts less the distances. What is the best least distortion map from a piece of the sphere to a piece of the plane? So same kind of question. So now if I want to put this bigger, I want to remain on the same page, but make it bigger.
From
From here, okay. Okay, thank you. Yes, okay, very good. No, before. Yes, okay. No. Okay. Okay, so now I want to give the mathematics behind this, and I mean, mathematics we start with precise definitions, and this definition is was given by Thurston, another Fields medalist also, in a paper he wrote in 1985. So this is 40 years ago. I read that paper, and the paper is at the same time very difficult and very simple. It's very simple because you can read it. There's no reference to any theory. In fact, you don't need to know complicated theory. There are almost no references. There's no reference to another paper. It's self-contained. You can read it. It contains only basic mathematics, but it's a difficult paper because you have to imagine. You have to work by yourself. In fact, you cannot find. I mean, today you can find references in other papers, but at that time it was very new. So it starts by the following definition. You have a surface S equipped with two hyperbolic metrics. I will talk about hyperbolic metrics later, but now, so these are metrics of negative curvature. The fact that they are metrics of negative curvature is not important now for what I will say. There are two surfaces equipped with metrics. You have two metric spaces, and the metric spaces are surfaces, and you have a map between them. So the map is between the same surface equipped with the first metric and the second surface equipped with the second metric. And then there's something which you call naturally the Lipschitz constant of this map. This is also a classical definition. What is Lipschitz? So in general, so you measure the distance between the images, the distance between the two images, and you divide by the distance between the 2 points. So in the images you use the second metric h. For the points you use the first metric g. So you have a map from SG to SH, and in general you have I mean, all of you, I think, when you learned about metric spaces, you heard about Lipschitz. A Lipschitz map. A Lipschitz map is when the supremum over all pairs of points of this ratio here is bounded. If the supremum is bounded, then you say that the map is a Lipschitz map. And now, so this is the Lipschitz constant of phi. For instance, if the map is differentiable, since let's take compact surfaces here. Compact surfaces, I didn't say, but let's compact. If the map is differentiable, then the Lipschitz constant is always finite. This is a basic theorem. Okay, and now I want to define a distance between the two surfaces, the two hyperbolic surfaces, the two surfaces equipped with different metrics. And you say that the distance between these two surfaces, SG and SH, well, it is the infimum of this Lipschitz constant of phi, and you take the infimum over all possible maps phi. I said map phi homotopic to the identity. If you don't know about homotopy, don't worry about this. But you have two surfaces which are homeomorphic, since I said the same surface equipped with two different metrics, and you say that the Lipschitz map you take only Lipschitz map, and you say that the distance between the two surfaces is the infimum of the Lipschitz constants of all maps between these two surfaces. So if you think about the picture we had at the beginning, you can ask the question, okay, what is the distance between the first fish and the second fish? And the map, which was suggested by the grid, will give you an idea of what is the best map between the two surfaces, and then you compute the Lipschitz constant of this best map, and this will be the distance between the two surfaces. So in conclusion, we are putting a distance function on spaces of surfaces. And in my title and in the summary of the course, I talked about Thurston distance, and the Thurston distance is exactly this distance between surfaces. You take the best Lipschitz map between them, and you well, you have to take logarithm for no. I mean, it's not very important, but you have to take the logarithm. The logarithm of this infimum here will be the distance between the two surfaces. So I said infimum over homeomorphism, homotopic to the identity. We don't care about this now. And so the Teichmüller space of S, which I will talk about, it's a space of all metrics on the surface, more or less. I will give a better definition later, but this is a space of all metrics on S, and then you get a metric. This space becomes a metric space because you are measuring distances between the surface S equipped with various metrics. So this makes this space of metrics itself a metric space, and this is the Teichmüller space equipped with the Thurston metric. So I talked about this paper of Thurston. It's this one here, 1985. It's called Minimal Lipschitz Maps Between Hyperbolic Surfaces. So now, from what I said, you understand more or less all these words here. It remained a preprint until recently, 2022, where it was printed in Thurston's collected works. But the preprint, you can find it on the internet. They published the preprint in the internet without any change. Yes, tell me, please.
What is the leap by less than 1? Then, I mean,
this is a very good question, but this is special to hyperbolic geometry. The Lipschitz constant can never be less than 1. If the Lipschitz constant is equal to 1, this is one of the propositions, of the first propositions in this, because we are talking about hyperbolic metrics. I will explain several analogues of this Thurston metric on various spaces, in fact, and there will be spaces of Euclidean structures. But here you have to say something about the Euclidean structure so that this Lipschitz constant is never less than 1. This is a very good question. Yes, it's one of the propositions in Thurston's paper, one of the first propositions, that this Lipschitz constant is always greater or equal to 1.
Your best map is the minimal Lipschitz map?
My best map is what? Yes, minimal Lipschitz map. The minimal Lipschitz map is the best map which I talked about. Okay, so now okay, so this is second. No, this is the fourth page. So as I just suggested, there are many possible generalizations. So the theory of hyperbolic surfaces with boundary, this is something different, a different theory. So when you have a paper like this, then you ask, as a mathematician, you have many questions. Some of them are good questions. What happens if the surface has a boundary? It turns out that the theory for surfaces with boundary is different from the theory for surfaces without boundary. I will talk about this. And then surface with funnels, this is proper to hyperbolic geometry. I'll explain to you what are surfaces of funnel. Surfaces of infinite type, so in fact this is also some very natural setting for this kind of theory. Euclidean surfaces, surfaces equipped with Euclidean structure. So surprisingly, the theory for Euclidean surfaces, which is easier than the theory for hyperbolic surfaces, people started working on it very recently. In fact, they asked the right questions and they developed that. So here I think I gave some. So I gave mostly. I told you I wrote on this. I worked on this for 40 years with students and colleagues and so on. So I know more my work than the work of others because I understand I understand it more easily. My papers. So these are recent. I'm just giving you a list of papers to tell you that this is a very living subject. In fact. So this is a paper 2025 called Minimal Stretch Mass Between Euclidean Triangles. So the surfaces, so I started with this complicated picture of fish. And then I talked about hyperbolic surfaces, but now if you take, if your surface is just a Euclidean triangle, so in other words, my space is the space of all triangles in the plane. And I want to put a metric on this space of triangles in the plane. And I want to study the properties of this metric, and there are a lot of very good questions on this space. For instance, let me come here. Let me come back here. You see, you are studying. Sorry. You are studying. You want to study best maps between this fish and this fish, and okay, this is suggestive picture by a non-mathematician whose mathematical intuition is a very, very profound intuition. So he said, okay, the best map between these fishes is probably this one with this grid, this rectangular grid transformed into this grid. And then I mentioned the name transformation, you know. So how do you pass? What is, if we believe that okay, nature takes always the simplest path, if so this is a hypothesis, if there was if evolution, a certain evolution theory which is I mean interesting, this fish by an evolution became this fish. What are all the steps of this evolution? What is a natural, the most natural and the most energy minimizing path between this family of fish and this family of fish? So when I go here again to this paper on Euclidean triangles, so you may ask the same question, okay, so you put a distance on the space of triangles, which I talked about. It turns out that you have, I mean, it's interesting and important to consider only triangles of the same area. If you multiply the triangle by a constant, then you get you want to consider the triangle as similar to the first one. So this is a metric on between Euclidean triangles up to homotity. Okay. It turns out that this and you want to, so when you define a metric on this space of triangles, then there are Very good questions. There are very good questions on this metric space. You can ask, for instance, can you describe geodesics for this metric? Meaning, can you describe shortest paths from going to one triangle to another triangle? It's a path constituted of a family of triangles, but it's shortest path among all the paths that I can draw between the two triangles. It turns out when you define a metric, a good question is to know whether this metric is a Riemannian metric. This is for mathematics students, because there are some, if you know a little bit of Riemannian geometry, is this metric given by an infinitesimal form, or and so on and so on. So we studied, this is first paper I wrote on this with a Turkish postdoc who came to work with me, and then it turns out that this theory works well for acute triangles. If you take all the triangles in the plane, including the non-acute triangles, then there are several questions which we don't know how to solve. So if you read this paper, and if you have ideas on, more general, on the space of more general triangles, this is very good. And then I have, then there are several other papers, and this is space of singular flat metrics. This is also on surfaces. So instead of the hyperbolic surfaces which Thurston started with, you can consider Euclidean metrics on a surface which is not a planar surface, but there's a theorem, there's a result in geometry, a basic result. If the surface is not the torus, you cannot put a Euclidean metric on it. But you can have Euclidean metrics with singularities. I will give examples later, I will give pictures. So, okay, so we said, okay, we want to consider surfaces of higher genus, not the torus, but with Euclidean singularities, with Euclidean metrics with singularities. So this is, it turns out you can say a lot of things, and there are a lot of open questions on this. Everything we know, we put it in this paper, but there are a lot of other questions which we did not touch because we are only two persons and we cannot work more than 24 hours a day, and we need other people to work on this. So this is also still a living subject. So here is also, so I mentioned that some of the metrics which you define, some of the metrics on spaces of metrics, turns out to be not Riemannian metrics, something weaker, which is called Finsler metrics. So the Finsler metrics have they have infinitesimal descriptions, and this is a paper also with my with my Chinese colleague Yi Wang and my Japanese colleague Kenichi Oshika. We study the infinitesimal structure of this space of metrics. So these are examples of things which are done on this work. So I want to talk about Euclidean metrics, which is something more familiar to you. But I want to talk also about the hyperbolic case, which is the initial setting of which Thurston started with. For this, I'm trying to follow now the program of these lectures. I said I will talk a little bit about hyperbolic geometry, so that you know a little bit what is this hyperbolic setting. So probably many of you know a little bit. I mean, probably students in mathematics know a little bit about hyperbolic geometry. But I will I will give more later. But now I want to give just a little glimpse into this this theory, which I like very much. So I said that I read the Lobachevsky and I wrote a book on his geometry, and I wrote also an article for Ganita Bharati on non-Euclidean geometry, which, if you are interested, you can. I mean, I'm not sure you can find it in the library here, because this journal is not. I mean, I think it's not very well known in India. I remember somebody told me, "Oh, I don't know this journal," a colleague of mine. Anyway, so they are. So let me say a few words of introduction today on hyperbolic geometry. So, okay, you know, people when they learn hyperbolic geometry, they start with models. I mean, you want to see what are the what are the lines for this geometry? So what is a geometry? In fact, to define a geometry, you have to define points and lines, and you start with this. Well, the lines means the straight lines. The straight lines in the Euclidean geometry. The straight lines in the Euclidean geometry are the shortest distance between points. In hyperbolic geometry, you have the straight lines, which are curved here, but they are straight lines of my geometry, which are the shortest path between 2 points. The straight lines, knowing the straight lines in a geometry means that you know everything, in fact, because the axioms of a geometry concern only points and lines. If you look at Euclid's axiom for Euclidean geometry, you have axioms between points and lines, and hyperbolic geometry is just a little modification of these axioms. And it has to do only with lines. Let me also tell you, as I said at the beginning, I read Lobachevsky, and in Lobachevsky there are no models. In fact, he was working he was doing all his work on hyperbolic geometry, which is a very profound work. In fact, he was computing areas, volumes of three-dimensional polyhedra in his geometry and so on, but he didn't know any of these models. So you don't need models, in fact. He was just thinking in terms of lines and axioms, and he developed the theory which, I mean, the development of Lobachevsky is more or less what we know now about this geometry. When they discovered the Euclidean models here, they didn't prove anything, almost anything more than what he knew.
He was working with the constant negative curvature, or? Constant,
yes, always, yes. No, always constant. So when I'm talking now,
I'm talking about Lobachevsky.
Lobachevsky only constant negative curvature. Of course, he was not talking about curvature. He didn't have this notion of curvature. It came from Gauss after him. But he was proving all the theorems about this geometry with lines and intersections of lines, and it was abstract. It was concrete, in fact, it's in mind, but without any model. So, but it's easier to work with models now, since you have these models came much later than they came 100 years after Lobachevsky. These models. Because we have formulas, you know, and I mean, most people like formulas. I cannot read formulas. In fact, I cannot work. I'm always embarrassed to say that formulas for me do not mean anything. I always think about using lines and I mean, not only in this theory, but in general. So anyway, so the easiest to, I mean, if I tell you, okay, here are the axioms of hyperbolic geometry, then after this, you tell me, okay, but what should I do with these axioms? But when you have the models, it's easier. So this is why I'm talking about models here. So this is, there are two main models. This is the disk model, and this is the upper half model. And in these models, the lines of the geometry have a description in terms of Euclidean geometry. So, for instance, in this model, the lines are arcs of circles which are perpendicular to the boundary. Arcs of circles which are perpendicular to the boundary, all of these. So, for instance, this diameter of the circle is also considered as a circle perpendicular to the boundary. You see, this is a picture of a collection of lines in the hyperbolic space. So if you are a geometer, then you said, okay, so I don't find here any triangle, but usually geometers, I mean, as a geometer, I like to see triangles. I don't see any triangle. Somebody sees a triangle here? This is this is a quadrilateral here. I can see a here is a small triangle. Here is a small triangle. You see this triangle? Okay, so I have a geometry with lines, and I have a triangle. A triangle is formed by three geodesics which intersect intersect pairwise. So yes, thank you. There's another one here. Thank you. I have here triangle. So, okay, as a geometer, I say, okay, this is a new geometry. So what would I do with this new geometry? And then you want to study properties of triangles. So the first question is, okay, I have three triangles. So I take what? I take the three altitudes of this triangle. And do they always meet in a single point, like in Euclidean geometry? The three perpendiculars. Yeah, I didn't tell you also that in this metric you can measure angles. You see, you can measure angles like in Euclidean geometry, and the angles are the same as the Euclidean angles for some obvious reason, but I don't want to talk about this now. So this angle is around. I don't know, maybe 65 degrees and so on. So you take this triangle, you draw the three angle bisectors, and you want to see whether they intersect in the same point as in Euclidean geometry, which is not at all obvious because it's not Euclidean geometry. And then you try a little bit, and you see, well, in the triangles I see that it's correct, and then you try to prove this. And this is a theorem, in fact, a proposition in hyperbolic geometry, that in any triangle, the three angle bisectors or the three altitudes meet at the same point. But it needs a proof. It doesn't follow at all from the Euclidean, I mean, from the same proposition in the Euclidean setting, right? So this is a new geometry, hyperbolic geometry. And so you have lines, you have angles, you have perpendiculars, and so on. And okay, this is another model. Another model. I don't see triangles here. I see quadrilaterals. So after, let's see. Yes. No. Where is this triangle? This arc, This arc?
Yeah.
Okay, and the second one is this one?
Yes, and the semicircle.
And the semicircle?
No, that one.
No. Yes, you are right. But this is a triangle where the vertices are at infinity.
Oh, yeah.
This is very important, but it's not what I'm. It turns out that in hyperbolic geometry you have. You have a good notion of what is at infinity. Here the infinity is this circle. Here the infinity. It's called the boundary at infinity of your space, and you have also triangles where whose vertice is at infinity, and they are very important, in fact. And Lobachevsky, without having any model, he talked about triangles which have angles at infinity, and the angles are zero. But here I don't find any on. But anyway, you have quadrilaterals, you have hexagons, and so on and so on. So this is what you do with hyperbolic geometry. Like with any kind of geometry, you want to study properties of triangles, quadrilaterals, and so on. There are many theorems in Euclidean geometry about quadrilaterals, and then you want to know whether the same theorem holds for hyperbolic geometry. Not all the theorems hold. Some of the theorems fail. You see, like obviously. The theorem which tells you that the Euclidean theorem which tells you that the angles in a triangle is always 180 degrees. This theorem fails in hyperbolic geometry. And if you want to understand, then it's not difficult, in fact, but it's one of the basic theorems in hyperbolic geometry, which Lobachevsky proved without any model, that the sum of the angles is always strictly less than 180 degrees. Okay, so these are the two models, and there are formulas. There are formulas for distances, which I didn't copy here. There are formulas for which you can compute distances between points and lengths of paths and so on, which we will see a little bit about them later. And now I said also that I said that I want to talk also. I put in my outline that I want to talk also about the geometry of the sphere. For several reasons, in fact. I already mentioned one reason, this theory of Best-Lipschitz maps, where you consider the Earth as spherical, and then you have a country here, like India, say, and you want to build a map of India. And what is, how do you do? How do you build this map? You want a map to be best Lipschitz map, but also to preserve some other things which I will talk about when I will talk about geographical maps. Euler has 3 long papers about this, and then other geometers, in fact, like Darboux, Chebyshev, and Lagrange. Several people wrote papers called on the construction of geographical maps. Mathematicians, I'm talking about mathematicians. Of course, geographers, there are thousands of papers about how to construct geographical maps, but if you look a little bit, not interesting. Most of them not interesting at all. Well, the papers of the mathematicians, at least you know what he's talking about. There are definitions and there are metrics, and you're talking about. Whereas the geographers, it's always mixed with. They make measurements. You see, I said that you are considering the Earth as spherical. But it's known, in fact, since Newton, that the Earth is not really spherical. It has the shape of an ellipsoid. In fact, it's a little bit flattened at the poles. So if I exaggerate, it's like this. It's more an ellipse of revolution. So it has, there's a rotational symmetry, but on the top and bottom it is flattened. I'm saying this because the people I mentioned, like Euler, they knew that the Earth was more ellipsoidal, and Euler wrote a paper which is not the three main papers I talked about, but another one on the geometry of the ellipsoid and how you measure distances on the ellipsoid, and properties of some triangles on the ellipsoid. He didn't know how to deal with all the triangles, but some of the triangles on the ellipsoid, mainly the triangles where one of the vertices is at the North Pole. I mean, at the North Pole, which is flat, where the surface is most flattened. So this is also something which is interesting, in fact. Everything I say about spherical geometry, if one wants to do the analog for the ellipsoid, then it's fine and it's interesting, I think. Euler started this, but I think nobody, I mean, no mathematician studied best Lipschitz maps from the ellipsoid to the plane after Euler. So okay, so here we have also on the sphere. So so I wrote here, you have a great circle, and these are small circles. So what is a circle here? A circle is just the intersection of the sphere with a plane. This is a fact of Euclidean geometry. When you intersect a sphere with a plane, you get a circle on the plane. So some of the planes pass through the origin, and others do not pass through the origin. If the plane of the circle passes through the origin, then it's called a great circle, because its radius is the biggest one, but it's also the great circles are the geodesics. The lines on the sphere, I told in the previous slide, I told you what are the lines in hyperbolic plane. The lines on the sphere are the great circles. The small circles are not lines. You see, when you take when you fly with an airplane from here, say from whatever, from here should maybe Helsinki to St. Petersburg. No, St. Petersburg is too close. From 2 points which are here and here, the shortest path is not at all this one here. This would be very long. The shortest path should be something like that. So for instance, to go from here to here, the shortest path is this one. This small circle is not at all the shortest path. So in spherical geometry, you have the lines are the great circles. So for instance, here, this is only great circles. You take 3 great circles. You have a triangle.
Segment of great circles, right? Segments of great.
Yeah, you are. Well, no, here I drew the three circles. You are right. The three great circles are the lines. No, they are called the lines. The segments of the segments of these lines, yes, you are right, are the shortest path between points. To find the distance, to compute the distance between this point and this point, one way is the length of this segment of a great circle joining them. This is what you're saying, right? In fact, there are 2 segments. One is this one here, and one is this one here. But you must take the shortest one between the two, the shortest length. So anyway, so you have spherical triangles. And you have angles. It turns out that the angles. First, you must ask the question: what is an angle? In fact, I have a geometry. I have a geometry with points and lines. So how do I get angles? What do angles mean? So you come back to Euclid. Euclid defines lines and points. He never defines angles, but he works with angles. And how does he get angles? This is a very good question, in fact. I invite you to think about this. Okay, so here I'm telling you that the angles, you get angles on the sphere, angles between lines, and these the angles are the same as in Euclidean geometry, which is not obvious, but you measure them in the same way. And for a triangle, you have three angles, and the sum of the three angles is always greater than 2 pi. This is a theorem also. I said that in Euclidean, in hyperbolic geometry, the sum is strictly less than 2 pi. Here the sum is always strictly greater than 2 pi. And then first, I mean, when you study this, the first thing, I mean, you want to know whether the elementary properties of Euclidean triangles are true in hyperbolic geometry. If I take a spherical triangle and I take the three perpendiculars from the sides to from the vertices to the sides, do they meet? Do they always meet in a single point? The answer is no, in fact. In spherical geometry, it doesn't always work, but there are conditions. In fact, so let me tell you one. So, okay, let's take, every one of you, I'm sure, who heard about the sphere and the geometry of the sphere, you know that the sphere has, you have triangles with three right angles, right? So here is one. Here is one segment of great circle here, and then take the one perpendicular to it that starts here, which is perpendicular also to the equator, and this is a piece of the equator, which is so this. Consider this spherical triangle with three right angles. Okay, and now I want to study. I want to answer my question about the three altitudes meeting in a unique point. So for this triangle, okay, I start from this point. Well, since this is perpendicular to the other side, this is an altitude, right? This is also an altitude because it's perpendicular. It goes from one vertex to perpendicular to the other side, and this is also an altitude. The sides are altitude, and they don't meet in one point, right? And I can take more complicated examples. I don't need this triangle with three right angles. It turns out that in spherical geometry, you have this theorem which tells you that if each of the three angles is less than a right angle, then the three altitudes meet in one point. So this is just an example to tell you that okay, this in spherical geometry you have also lines and triangles and so on. Some of the theorems of Euclidean geometry hold, some of them do not hold, some of them hold with some extra conditions like the one I just said. And you need to know about this when you want to study, and I will give you examples, when you want to study best Lipschitz maps from a surface to the other, from a hyperbolic surface to a hyperbolic surface, or from a spherical to spherical, you need to know a little bit about these theorems of non-Euclidean geometry. If you don't know them in advance, then you learn them at the same time. And I have my next slide here. Wait, I have my next slide. I will give you an example here. So we said we will stop for 5 minutes so that we. Yes. So no, I want to stop for 5 minutes and then yes.
So we are waiting for 5 minutes.
I wrote a few papers on this. I learned this with a colleague of mine in Basel. His name is Norbert Acampo. So there's a geometry which he gave it the name transition geometry, in fact, where you pass continuously from Euclidean to from hyperbolic, say, to Euclidean and then to spherical, continuous paths. And then you ask, okay, what are the theorems of one of these geometries, say Euclidean geometry, because you are more used to it, where you can pass continuously from one geometry to the other, and what happens in this continuous deformation. So somebody asked me here if the curvature is constant, negative, constant, or variable. We are talking about always constant curvature, but we are varying the geometry continuously. So what happens to the trigonometric formulas when we pass continuously from one geometry to the other? What happens, I mean, how do you, what happens to the geometry of the triangles, and so on and so on. So this is one other thing which I will not have time to talk about. But there is this question of transition between the three geometries. And this is why I like to talk about them together, in fact, the three geometries at the same time. So now this is something on spherical geometry, which is related to the problem I mentioned, the problem of finding best maps, best geographical maps. So we start with this proposition. Let's start with this one here, the second one. So I take a spherical triangle, ABC. I take D, the midpoint of this line AB, of this side AB, and E, the midpoint of this side BC, and I join them by a shortest arc, a geodesic, and then the theorems. The theorem in spherical geometry tells you that DE is strictly less than AC. In Euclidean geometry, if I take a triangle, Euclidean triangle, and then I take the line joining the middle, the midpoints, then I take an equality that DE is equal to half of AC. Right? In spherical geometry, there's a strict inequality. I mean, whatever triangle you say, big, small, angles, and so on, it's always greater. Okay. So why I'm talking about this now? I'm talking about this because it implies this first proposition here. This is a proposition which I mentioned before, that there is no map from a region of the sphere to the Euclidean plane which preserves distances up to scale. It means, in fact, that you cannot construct a geographic map where the scale is the same everywhere, right? It's just because suppose I want to make a map of India, then I take a triangle, like a triangle, the shortest lines between Bombay, Delhi, and Calcutta. This is a triangle. So I want to, on my map, I want these three distances. I want these three distances to be of the same scale on my map, right? Let's say 1 over 1,000. Okay, 1 over 10,000, or 1 over. But then I will always find, by taking the midpoint of this triangle, I will always find 2 points where the distance on the sphere compared to the distance on the plane will not be 1 over 10,000. or 100,000, right? So it means that there are no good geographical maps. There are no geographical maps which are where there is a similarity, yes. So when on a geographical map you find here 1 over 10,000, this is always a lie. In fact, it's not possible. And this is why geographers and mathematicians then say, okay, so what do we do with this? People need geographical maps. How do we deal with this? So they always try to find maps which are methods of constructing geographical maps which almost preserve the distances up to scale. So what does it mean, almost? And this is where you have to work, in fact, and this is where Euler described in his papers methods of constructing geographical maps, and he proved that okay, these are better than the ones we know, and so on and so on. So this is and this business of finding best geographical maps, it's the same question as finding best Lipschitz maps between surfaces. So we were talking about best Lipschitz maps between hyperbolic surfaces or between Euclidean surfaces and so on. Now if I mix the geometries, I have a geometry of positive curvature, the sphere, and then a geometry of the plane, then the question is how do I find best Lipschitz maps from parts of the between triangles, say. We forget about maps of complicated maps of countries, just between triangles. What is the best Lipschitz map between a spherical triangle and Euclidean triangle? Can I find a method? And does this method depend on the angles of the spherical triangles, if it has very large angles or very small angles, and so on? So this is part of what of the questions that are interesting in this theory. Okay, so now we come back to the original question by Thurston. So I wrote here. Okay, so I want to talk about ideal triangles, and Thurston's construction of best Lipschitz maps. The basic element, in fact, in this theory is the question this figure of an ideal triangle. So this is not an ideal triangle. An ideal triangle is here. And I will talk later about it, but first I want to say something about the other triangle. So this is a triangle where the 3 vertices are at infinity. This is an ideal triangle, this is an ideal triangle, this is an ideal triangle. I mean, all of these are ideal triangles. You see, I said I want to give an idea of hyperbolic geometry. So one of the basic things of hyperbolic geometry is the existence of these ideal triangles. Ideal triangles that is vertices are at infinity, and the angle at the vertices is 0. I talked about Lobachevsky at the beginning. Lobachevsky works with ideal triangles. In fact, he didn't have any model, but he understood and he knew that this very important ingredient in hyperbolic geometry, that you have triangles with where the angles are 0 and when the vertices are at infinity, and they play a major role in Thurston's theory. So another thing you have to know about ideal triangles is that this one and this one and this one, they are all isometric. What does it mean that they are isometric? It means that you have an isometry of the hyperbolic plane, an isometry of the whole space, which takes one triangle to another triangle. So there's an isometry which there's a rigid motion of this hyperbolic plane, which takes any for any pair of ideal triangles, there's a rigid motion of the space which takes this one to this one. How can you? I mean, there are. If you write, there are ways of doing this in models, but something which is true in hyperbolic geometry, and which is also true in spherical geometry, is that for a triangle, let's see here. No. Okay. Let's start with here. I wrote this proposition here. So good. So this is a triangle with 3 edges and 3 angles. The isometry type of this triangle is this is very easy. This is like in Euclidean geometry. This is not what I meant when I wrote this. I will tell you. So if I give you 3 in Euclidean geometry, if I give you 3 numbers which satisfy the triangle inequality, the 3 triangle inequality, then you have a Euclidean triangle with these 3 edges, right? And this triangle is unique. This is true also. This is what I'm saying here. This proposition it's not difficult to see, and it's not surprising that the 3 edges determine the triangle up to an isometry. The thing which is special to yes, you're right. Now I'm talking about, this is a second mistake here. This is hyperbolic. So I meant the proposition for the hyperbolic. It's also true in spherical, but I'm talking about hyperbolic. It's determined by the three edge lengths. But my first mistake, what I want to say here is that it's determined by the angles. The angles in a spherical in hyperbolic and in spherical geometry, the angles determine the sides. If you give the if two hyperbolic triangles have the same angles, then they are isometric. I will give you some trigonometric formulas, in fact, next time, which gives a precise this is a precise formula for the edges of the triangle in terms of the 3 angles. Yes?
Edge length thing is wrong also?
Excuse me?
Edge length. Is it wrong also?
Edge lengths? Yeah, it's true also for edge lengths. But
hyperbolic triangles are also determined by?
Are also determined by the edge lengths. But they are also determined by the angles. They are also determined by the angles. And this is what I meant here.
In Euclidean geometry, the angles don't determine
Exact. In Euclidean geometry, this is not correct. Yes, right. Right. In Euclidean geometry, the edge, the angles do not determine the triangle, but in hyperbolic and Euclidean, they determine. And why did I say this? I said this because, okay, I was looking at this picture. I said that all these triangles are isometric. In fact, not only they are isometric, but there's an isometry of the whole space, which sends one of these triangles to the other triangle. There's a rigid motion of the space, which sends any one of these, because they are all isometric, because they have 0 angles, and I just told you that the angles determine the sides. So 0 angles is fine. And okay, this is very. I mean, this is a very important property of these triangles, which are ideal triangles. And now the construction. I said that one of the themes here is the construction of best Lipschitz maps. So Thurston's theory starts with the construction of Lipschitz maps from a triangle, from an ideal triangle to an ideal triangle. This picture is taken from Thurston's paper. So okay, so this is an ideal triangle, a triangle with 3 zero angles. The lengths of the sides are infinite. So it's also the fact that the sides determine the triangle. I have 3 infinite sides, so there's only one ideal triangle. Since the sides are equal, 3 of them are infinity. So okay, so now and this is an important ingredient in this theory. This is a very important ingredient. I should have made another picture, but it's fine. So suppose this triangle is sitting in the hyperbolic disk. Okay. So now these pieces here of circles, this is special to Euclidean hyperbolic geometry. You have lines which are called horocycles. The horocycles in the hyperbolic plane are the Euclidean, in this model, they are the Euclidean circles which are tangent to the boundary. Okay, so imagine here these pieces, all these pieces of horocycles are pieces of circles in the hyperbolic space which are tangent to the boundary. Tangent from the Euclidean in the Euclidean sense. They make zero angle with the boundary circle, with the boundary at infinity of the space. Okay, and you have to imagine that there's you see you start taking a small horocycle, then you make it bigger and bigger and bigger and bigger and bigger and bigger, and you do this at the same time from the 3 sides. You do this at the same time, the same velocity of making it bigger and bigger. So it's more or less clear that these circles will, there is some point, because of the symmetry, there is some point there are 3 points on the sides where you cannot make it bigger. Okay, so this is called the horocyclic foliation of the ideal triangle. And since, as I said before, there's only one ideal triangle up to isometry. So, for instance, this one here, which is the most symmetric one, when I draw it in this Euclidean model. So you start here, more and more and more from these sides. So there's a unique. On each side there's a unique point where you stop. This here, and this one here, and this one here. So this figure will be valid for any ideal triangle, since they are all the same. They are all isometric. There's no difference between one or the other. There's a rigid motion of the space which takes me any ideal triangle to the other. So okay, so I get these fields of lines here, the 3 fields of lines, are called a foliation. So a foliation is just a set. A foliation is just a set of lines like this, like a vector field, but without orientation. You know what is a vector field, right? So a foliation is just a vector field with no orientation. So you have this foliation. You have this foliation which do not cover the whole Euclidean, the whole. Well, here it's a hyperbolic triangle. It covers it except for a small region here, and it's a foliation by horocycles, pieces of horocycles. Okay? Now, the map that Thurston defines is, this is distance t, hyperbolic distance from this distinguished point. There are 3 distinguished points on the boundary. I want to send this piece of horocycle to a horocycle which is at distance k times t. So the first one is fixed because k times 0 is 0. The first one is fixed, but this one here at some positive distance t is taken to this one, and so on. So this defines, this tells me where I send each horocycle, each piece of horocycle, and then I make the map. So on each horocycle, I make it just distance preserving up to scale. So I told you now where each horocycle goes, and I told you on each horocycle what is the image of each point, since this length must be going from this piece of horocycle to this piece of horocycle. It's I take the most obvious linear map.
So here angle dividers meet at one.
I don't. There are no angles here. I mean, the angles these are always perpendicular. Perpendicular, yeah, they are perpendicular because.
Dividers meet
what dividers?
those lines.
The dotted lines.
Ah, yes, the dotted lines. I'm not using them, but what do you want to do with this? Yeah, they are preserved. They are preserved. Yes, it sends the middle to the middle. Yes, it sends the middle point to the middle point. You are right. You are right.
Happens in only hyperbolic and Euclidean, not spherical.
In Euclidean, this and spherical, you cannot do such things because you don't have horocycles. So you have to invent something else, and you don't have ideal triangles also. So this is why the Euclidean theory is completely different, and the spherical theory also is different. This construction is the most basic construction in this paper of Thurston, of which I gave you the reference. Yes.
Giving the definition of a Lipschitz map.
Yes.
In a particular case.
Yes.
So far, you have not defined it in general.
No, only in this particular case. And I'm saying that this construction here is the basic construction in Thurston's paper, because I want to I have this picture here. This picture here. This picture also is taken from Thurston's paper. So you see so here it's not very clear, but here you see this. There is each time you see something like this, a small triangle. This is the central triangle of an ideal triangle. So one basic fact of hyperbolic geometry. This is a surface. This is a surface without boundary of genus 2. You can cover any surface by a union of ideal triangles. So the ideal triangles, you see here it becomes thinner and thinner, and it wraps around. It wraps around infinitely. I mean, it goes. I mean, one of the basic things to understand about the hyperbolic geometry is to see how can you divide a surface? How can you divide a surface into a union of Euclidean of hyperbolic ideal triangles? Finitely many, because it's a compact surface, and each Euclidean, each ideal triangle has a definite area, which is the area of one of them, of any one of them, since they are all isometric, and so they must add up to make the area of the surface.
So you are partitioning the surface?
Yes, I am partitioning the surface into these ideal triangles. So this may be easier here. This is a surface. This is a picture which which I made. It's not from. So you see, there are many ways of partitioning the surface. There are many ways of partitioning the surface. For instance, okay, you see, this is a surface which is a sphere with 3 holes. And if I take now look only on the topology, if I glue 2 of them, I get like above a surface with no boundary and with 2 holes like this, a surface of genus 2. Okay, so now this one, maybe it's easier to see. So this is also of course, this is only symbolic. I mean, you just to see how how the ideal triangles wrap around this boundary. So they are big. One of them is here. You can see the thick part in front of you. The other one is on the other side of the surface. And the sides, they spiral along the boundary component, which is a geodesic. This is also part of the theory of hyperbolic surfaces. Any hyperbolic surface, if I take one closed geodesic here, one closed geodesic here, and one closed geodesic here, and if I cut the surface along these closed geodesics, I get 2 surfaces homomorphic to this one with geodesic boundary, and each one I can geometrically, each one is the union of 2 ideal triangles which spiral along the boundary. You don't need to know much about hyperbolic geometry, but this is one of the basic things that you have to know when you and it's always used in this theory that okay, any surface, any hyperbolic surface, any hyperbolic surface can be divided into a union of hyperbolic ideal triangles. Yes, please.
Does it mean that all these surfaces you are taking any quotient of the upper half plane by isometric group of that styling?
Yes, exact. Yes, because when you take the universal cover of this, you get all these ideal triangles like this one here. Yes, these ideal triangles which you draw here, they are covered by genuine ideal triangles in the universal covering. So Professor Shah will say something. Will give something about universal coverings. You talk about universal and so on. So this is so okay. So just I have to conclude now. So the basic thing about Thurston's theory is that this map here, between ideal triangles, it has a meaning when the surface is decomposed into ideal triangles, and it is the model of his best Lipschitz map. This is a best Lipschitz map. This Lipschitz map between ideal triangles, or a Lipschitz map from one ideal triangle to another, is the model, the absolute model for this best Lipschitz maps between the hyperbolic surfaces.
In this particular example, the map is defined from where to where?
The map is defined from this ideal triangle to itself, but it could be also defined from one ideal triangle to another one. Yes, yes. And here, maybe I didn't say, it's the identity on this central. So this is why, let me end with this. This is why this map, this Thurston map, which is the best Lipschitz map between hyperbolic surface, I mean, it cannot be used as a map for in geography because for geography, you want the map to be, when I tell you that this map is best Lipschitz, in fact, in hyperbolic geometry, here it's the identity. So I can make it a little bit better if I want the Lipschitz constant to be constant everywhere. And this is what we want in geography. You want the distortion of the distances to be the same everywhere. You want it to be equally distributed everywhere, in fact. This is why in geography, I mean, the problems are the same, but what you want is something different. And I will talk about this. I think one of the days I have announced a lecture on geography. Okay. Yes? Huh?
What was the main statement for this?
For this one, okay, okay, you are right. In fact, the main statement is just a heuristic statement, which says that Thurston's best Lipschitz maps, of which I talked about in the definition, are like this. They are maps between ideal triangles, which when you glue them together, they give you best Lipschitz maps between surfaces.
Let's thank Professor Ratana.
Thank you.
And,
Thank you.
Now we go, so I think we have had enough questions and we are late, so we go down for tea and you can ask if you want, otherwise tomorrow also you'll be here. And 4:30 there is elementary talk on the which I will give on the board. And we go down for tea to the lawn, so tea and snacks, and then we come back here sharp. Because we have to maintain time because it's on YouTube, so we cannot extend beyond 4 and we have to start it. Okay, so I am only going to do 1 hour talk on fundamental group, and typically since it's only an hour, I can't do much more than introducing it and giving you some examples. But I'll also talk about homotopy of maps because he used homotopy, if you see. So let's start with some notations. So first of all, we'll denote by I, which is an interval from 0 to 1, closed interval. It has usual topology inherited from the metric on R, right? So that's the usual distance metric. So when I say I, it means this interval 0, 1 and the topology on it, which is the usual topology inherited from R, okay? And everybody knows topological spaces, so I'll be using that. I will not particularly be using metric space, but metric gives you a topology, as you know. The topology on a metric space is the topology which is generated by open balls. So let's say every set is, the set is open if it's a union of open balls. So if you have, so I won't write too much, but so if I have, all my functions will be typically continuous functions from one topological space to another, or from I to the topological space X, which would be like it would be called a path, or from X to Y. So let's say you have two continuous map f g from x to y, which are continuous, then you say f is homotopic to G. This means f is homotopic to G if there exists a function f, capital F, from x cross I to y, which is continuous. So x cross I has a product topology coming from x and interval I, such that fx0 gives you, so this is a continuous function, and such that fx0 gives you small fx and fx1 gives you gx for every, oh, so this should be capital F, sorry, for every x below. And the function f is called a homotopy between f, small f and small g, okay. So this is called a homotopy. So let's see, and first of all you may want to see some example. So if I take let's say your x is Rn, okay, and if I take y also is Rn, and if I have a function f from Rn to Rn continuous, another function g also continuous, take your pick. Let's say fx is a linear map, f is a linear map, g is a linear map, or f is just a shift map, any continuous map, or a constant map, identity map, doesn't matter. I would say f is homotopic to g. And the reason is because your Rn is convex, so you can define capital F from Rn cross I to Rn, which is going to be fxt equal to, you take convex combination of fx and gx. So where t belongs to, so x belongs to Rn and t belongs to 0. So this is a continuous map because it's a convex combination of two continuous functions, and you can see that fx0 gives you t equal to 0, so fx, and fx1 gives you gx, right? So if you remember, Professor Papadopoulos said that you take maps which are homotopic to identity, right? So since all maps from Rn to Rn are homotopic to each other, every continuous map from Rn to Rn is homotopic to identity, even constant map. And not just Rn, you can take a function which is you can take any convex space x subset Rn which is convex, then any continuous map from x to x is homotopic to identity. Means two continuous maps from x to x are homotopic to identity. If you take x a convex space and y a convex space in Rn, or in Rn and Rm, you can still do the same thing. So as you can see, this is an equivalence relation because, so two maps being homotopic, F is homotopic to G is an equivalence relation because for F, small f, F is homotopic to F because you can take fxt equal to just fx and you will get, for every t you just take fx, so you get this that F is homotopic to F is homotopic to G. You can interchange homotopy between G and F, but if you have F as homotopy from F to G, then you take some H, which is hxt is going to be fx1 minus t, so it will interchange F and G. And you can do also, so you got reflexive, symmetric and transitive. Transitive, for transitive, what you do is you compress, so x cross 0 half, you 0 half you expand to 0 1 and you double the size of your map, and I mean you go faster. So suppose you have F is homotopic to G and G is homotopic to H, then you have here one homotopy F and G, then you define H xt equal to fx 2t where 0 less than for all x in x, and g x 2t minus 1 half less than t less than or equal to 1. So, and these are, you know, mapped from 0 up to 0 1 and combination with f and g, they are continuous, and by gluing lemma you can prove that it is continuous, H is continuous, and you can see the lower line is F and the upper line is H. So this will imply that F is homotopy. Okay, so homotopy is an important relation. Now you have homotopy between maps, but you can also have homotopy between two, so you can say two topological spaces have same homotopy type. So let's say, can I write here? Will it be visible? So you have x is x, and so x and y have same homotopy type. So these are two topological spaces. If you have a function f from x to y and g from y to x, so these are continuous, so two continuous functions such that f composite g is, so now this is a map from y to y, is homotopic to identity map of y, and G composite F map of identity X. So this one is homotopic to identity X and this is homotopic to identity Y. Okay, so what does it mean? So this again you can say it is an equivalence relation because X is homotopic to X because you can just take identity map from X to X, right? And then F is homatopic to G, and then because this relation is symmetric, you can see G is homotopic to F. And you can also show that F is, sorry, so if X, so if you have X and Y are same homotopic type, then this relation is symmetric, so you can say Y and X are also same homotopic type. have same homotopy type. So let's see, the interesting thing is that Rn is homotopic to a singleton set, let's say some x0. You can also just, this is, okay. The other thing is, if you have that two spaces are homeomorphic with a homeomorphism F, then they both are of homotopy, same homotopy, because you have F and F inverse. F composite F inverse is identity and F inverse composite F is identity. So this one is beyond. So if the spaces are homeomorphic, then they have same homotopy type, but same homotopy type need not imply that they are homeomorphic. For example, this is a singleton set and this is an infinite set, Rn with the usual topology. They have same homotopy type. So how do you say, okay, instead of this I can just write 0 because they are homeomorphic to each other, right? So these two have same homotopy type, and so now you take a map F from Rn to 0. Maybe I'll just divide this, which is just a constant map, Fx equal to 0, and you take G from 0 to Rn, which is again just 0 going to 0, right? So, and now what do you get? F composite G is a map from 0 to 0, right? And F composite G is identity. And G composite F, what happens? Which is a map from Rn to Rn. So this is a constant map and it is continuous. This of course is just from one point to set to Rn, so it's going to continuous. G composite F is going to give you what? For every x, Fx goes to 0 and 0, right? So this is a map, again it's a constant map, equal to C0 on Rn, means a constant map which takes everything to 0. Now we learned that every map on Rn is homotopic, every continuous map on Rn is homotopic to every other continuous map. In particular, G composite F, constant map is homotopic to identity. So you get Rn and point singleton have same homotopy types, but you know that they cannot be homeomorphic, right? So okay, let me give you one more example, which is x equal to S1 cross I, which is an annulus. S1 is unit circle and you're multiplying with 0, 1. So that gives you an annulus in R2, right? And y equal to S1. Then this is example 2, this is example 1. So now f you take as x comma t going to just x, okay, and so this is continuous because it's a projection. This has product topology and this. So G from S1 to S1 cross I, you just take Gx equal to Gx0, right? Now it is easy to see that f and g, sorry, so not g here, gx is gx0 for x belongs to S1, here xt belongs to x. So f composite G is a map from S1 to S1, right? And its identity you can check. And G composite F is a map from x to x, which is Rn cross I x to x, which, what does it give you? So G composite F is the first of all F, so xt goes to x and then it goes to 0. So G composite F xt is x0, right? Now this one is identity, but this one you need a map from x. So you need G composite F. So you need a function, sorry, F x t1 t2. So this is your x, and this is a map from x cross I to x, which you take is, I think this should work, let's see. So x t1 t2. So you get that f x t1 0 equal to x t1 is 0, this t2 is 0, so you get x0. So this is G composite F, and fx1 t1 1 is xt1, which is identity. So this will give you, so this is easy to check, F is continuous and capital F is continuous, and the 0 line go to G composite F and 1 line goes to this. Okay. You can also do similar thing for R2 minus 0 and S1. Okay. So you can do this exercise, find that those are example, this is exercise that R2 minus 0 is same homotopy type as S1. You can do this, and you can, that means this and S1 cross I and S1, all three of them are same homotopy. Okay, now we'll talk about homotopy of path. Okay, so let me talk about, okay, so in the same way you can also do, if you have maps from G from x to so let's say f0 f1 continuous and g0 g1 continuous from y to z, and if you have that f0 is homotopic to f1, g0 is homotopic to g1, this implies that g0 composite f0 is homotopic to g1 composite f1, and you can also interchange, you can put f1 here and f0 here, so on and so forth. Okay, that's easy to check. These will be maps from x to z. Okay, so I'm not doing more of that, but let's see now. Oh, I'm going the wrong way. Okay, so a space is said to be contractible so space X is said, so topological space X is said to be contractible if the identity map from X to X is homotopic to a constant map. Okay, so for example Rn is contractible as we saw already, and you can also see any convex subset of Rn. So I am typically talking about Euclidean geometry, but when sir uses fundamental group, it will be for hyperbolic spaces, but definitions will not change. Okay, so, and you can say that the space is contractible, X is contractible if and only if if and only if it has same homotopy type as constant as singleton set, sorry. Okay, it's easy to show. You can use back and forth, it's not difficult at all. Okay, now what we are mainly interested is in defining fundamental groups, so we would use path homotopy. And path homotopy is, so first of all, paths. So a path is a continuous map from, so path in a topological space X is a continuous map from, let's say, alpha from I to X. That's it. And you say path between x0 and x1 in X is a continuous map alpha from I interval I to X such that alpha 0 is x0 and alpha 1 equal to x1. So now you know, so if you have a path connected space, then every 2 point can be joined by a continuous path, right? So you have lots of paths between 2 points, between different points, but there could be more path between 2 points, right? So for example, in R2 I can draw, I put one x0 here and one x1 here. I have one straight line path, or I can go like this, or I can go like this, or I can go like this. No, I mean, there's lots of paths. In fact, you can say there are uncountably many paths, right? So for any angle you can choose a path and put it, right? So now we say a path homotopy. So a path homotopy we define. So if I have two paths, let's say alpha and beta from x0, from I to x, so these are continuous maps, right, such that they have same beginning and end point. So let's say x0 to x1, this is my x, and I have one path alpha and another path beta. I put an arrow, means it starts at 0 from here and ends at 1 here. So alpha is path homotopic to beta, okay, which is with a dot path homotopy. If you have like homotopy, but it should be little extra. So now your I is original space x and x is y. So there exists a continuous function I cross I to x such that ft10 is alpha t1, ft11 is beta t1, and f0 t2 is x0, and f1 t2 is x1. Because I cross I is convex, I mean I is convex and I cross I is also convex, unless I put this extra thing, every path will be homotopic to a single constant path. So just talking homotopy for path is not enough, so you have to put this condition, and you can draw like this is your I cross I, right? So this is 0, 0, 1, 0, 1, 1, 0, 1. So this is your I cross I. X is 0, y is 1. Okay. And you have a space x, and you have point x0 to x1. So this is alpha and this is beta in this order. So what you do, what it says is this one goes to alpha, right? This one goes to beta, and the whole this line goes to x1, just the point, and whole this line goes to x0. Sorry. So let's. So this line segment. So this is a copy of this here, and these things are pinched to put to x0 and x1. So if I vary these things, typically I can show that these are all these in a different way going there. Of course, it can be going here and coming back also. I mean, it could be just, this is a, you know, heuristic picture. So now the main point about the 2 paths, to say that they are homotopic, for the first condition is their beginning point should be same, their end point should be same. Then only you can define path homotopy, otherwise you cannot define, right? And the second thing is that again you can say that remark. So what you say is that during homotopy this beginning point and end point remain fixed, okay, and all these lines define paths from x0 to x1, right? Isn't it? Because this line goes to x0, this line goes to x1, and if I take a fixed line or even a curve here like this, its image is going to be, because you can, this f is continuous, so if you restrict, you get a continuous map to that, any of these lines or this, and you get a continuous path from x0 to x1, path is continuous. Okay. Now similarly, as we said that homotopy is an equivalence relation, path homotopy is an equivalence relation. Relation between paths from x0 to x1. Okay, so of course their endpoints have to be fixed, otherwise I cannot define equivalence, the path homotopy. So for alpha you will say f t1 t2 is just alpha t1, that will give you alpha is homotopic to alpha. And if you have alpha is homotopic to beta, and then you want to say beta is path homotopic to alpha, you just interchange ft1 t2. So gt1 t2 will be ft1 1 minus t2, that will give you. Now and for three things you compress your f. So suppose you have f and g. So this is my I cross I expand this to, so this is I cross 0 half and I cross half 1, and I put f here and g here to get h, okay. So combine. I'm not giving you more information because I need to do many things. So let me just now put, so maybe I'll remove this, but before that I might want to say that just one little thing, that if I have f from x to y, and continuous map. And if I have two parts alpha and beta from I to x, such that alpha is path homotopic to beta, so it's this homotopy with a dot is the notation for path homotopic. When you write this, it means that their beginning points are same for alpha beta and end points are same for alpha beta. Then you can show that f is composite alpha is path homotopic to f composite beta. Okay, same way as you have homotopy between alpha and beta for x, you just compose it with f and you will get. Sorry, so I don't know that half is here, but it doesn't even look like square first. Believe me, when I say it, so here, and so see, this is 0 to 1/4, 1/4 to half, half to 1, okay, and this is 0 to half, half to 3/4, and 3/4 to 1, so this is alpha, beta, gamma, and you can suitably expand. So this will be alpha, this will be beta, this will be gamma, and you keep doing this, and you will get, so these two together, these two makes it beta gamma with alpha, and this is alpha beta with gamma. Okay, so this is the homotopy there. Okay, I think most of you know these stuff. So let's say this is fits. So yeah. So point is, now how do you define a group? You have associativity, you have inverse, but inverse gives you two different points. So what you do is you take closed paths and then define. Means you start a path from a point and end at that same point. Okay. For example, in R2, you can just draw a loop, right? A path which is starting at point x0 and ending at point x0. So I should hurry up, my time is almost over. So alpha is a closed path, I to x continuous, such that alpha 0 equal to alpha 1 equal to, let's say, x0. Now you can see you get a group, because so what is fundamental equivalence classes of alpha, such that, so these are paths which such that alpha 0 equal to alpha 1 equal to point x0. So these are continuous map from I to x, such that two endpoints go to 0 and 1 go to the same point. Okay. Now this is a group. Why? Because we will take alpha alpha inverse, this is same as alpha alpha inverse is Ex0, and this is same as alpha inverse alpha as Ex0, because x0 and x1 are same. So you have inverse, you have associativity, right, and you have the group operation alpha beta, because all paths are starting from x0 to x0. Like you have alpha, here is x0, and you have, let's say, beta. So you go alpha, so this is your beta. So you go double the speed alpha and then you go double the speed beta, you can do alpha beta. It need not be abelian, but if alpha and beta commute, then it will be abelian, which happens in groups. If your base topological space is a group, then it happens. So Now, if your space is path connected, so suppose I have, so this defines what is called a fundamental group, and it uses this, so for example, for fundamental group of Rn will be trivial because you can, because of convexity, you can find homotopy between the constant path at x0 and any path. So like if alpha, so let's just quickly do, if Rn, so if I have alpha, let's say path, so x0 belongs to Rn, and alpha is a path from I to x such that alpha 0 equal to alpha 1 equal to x0 in Rn, and this is continuous, then you can define homotopy f T1 T2 is going to be alpha, what will you do? So let's say 1 minus T2 alpha T1 plus T2 EX 0. Okay. This just means that the point T2 is multiplied to x0, and that's your point. So now this is a continuous map homotopy. Now ft1 0 is alpha t1 and ft2 t1 1 is ex0, and you can see that if I put t1 as 0, then this is x0, so it's a combination of x0, convex combination, so you will get x0 and 1 also you can see. So any path, co-closed path in alpha is path homotopic to a constant path, then you get that pi 1 Rn is trivial, is ex0. Sorry, okay, but this is independent of x0, right? I can start at any x0 and I'll get. Now, if you have a path connected space, you can show, so suppose I have a path, so I take paths at x0 and I have one other point x1, and I want to consider what happens if I take fundamental group here and here. So I can take, because it's path connected, I can take a path gamma, and I can consider this as path gamma inverse alpha and then gamma, that becomes a path at x1. So this is a, so given any path gamma, you get gamma hash from pi 1 x x0 to pi 1 x x1, which is just going to, so if I take any alpha that maps to gamma inverse, so this map gamma is actually this way, so gamma inverse alpha gamma, and this gives, actually one can check it's a group homomorphism and it's an isomorphism because it has an inverse also, gamma hash inverse will become the inverse. So it's, so in a path connected space, fundamental group is uniquely defined at every point, it's the same, they are isomorphic, so you just say fundamental group of that space, that surface, okay. So now I have to stop because we have 5 minutes over time, but let me see if, so if you have that they are okay, so if you have a map f from x to y, okay, there I can, then you can define a map f star from pi 1 x x2 phi 1 y fx. So if you have a continuous map f from x to y continuous, then you can define f star from pi 1 x0 to pi 1 y fx0 such that, so that is defined as f star alpha is f composite alpha, okay. And this is a group homomorphism you can see, and because alpha beta will go f star f composite alpha beta, which is actually, since alpha and beta are like double the speed and you are a composite, it will give you f composite alpha and f composite beta. So this is a group homomorphism, okay. And you can show that if two surfaces are, two topological spaces are of same homotopy type, and of course they are all path connected, then their fundamental groups are isomorphic by using the maps f and g and so on, which will give you f star g star, and then you will get identity and stuff like that. So for example, S1, which I am not going into, but fundamental group of S1 is the group of integer z, and then you saw that S1 cross I are 2 minus 0, they are all of same homotopy type, right, all of them. So they all have fundamental group S1, and so there are many surfaces, like if you take figure 8, fundamental group is going to be free group on 2 generator and it is non-abelian, and but if your base space is a topological group means it's a topological space but group operations are continuous, then fundamental group is always abelian, okay. And we will tomorrow do covering space and connect fundamental group with covering space. So now you saw S1 as Z, but if I do S1 cross S1 m times, then it will be Z cross Z cross Z m times, you can show that, and so fundamental group just get multiplied. But S1 has one hole, right, in the sense, so the surfaces with one hole in Euclidean space, more or less you can show that they have same fundamental, but there is a long theory about this. But when he says surface with genus G, means it has sort of G number of holes, okay. So I'll stop here, and if you have any questions you can ask me now or you can ask me later. Yeah, I think there are no questions on the YouTube, right? So maybe I should. Yeah. Yeah. Yes, because A, B and 0, 1 are homeomorphic, so you can change, you can replace 0, 1 with any interval A, B, but you just want to be consistent, so it's convenient to use I, because you see for path also, when you say path connected, you can use any interval A, B, but we use, I mean it's a continuous, there is a homeomorphism between I and A, B. Yes. No, then what are the endpoints? So yeah, anything is allowed. You can go alpha like this, and you can, so this is your alpha, you can go beta like this also. Continuous, it should be continuous. You can also do like alpha This is also a path, right? All you need is continuity. The other thing is actually when interval AB or 0, 1, when it's mapping, you are actually mapping your, so when you identify two endpoints, it's like it is a map from S1 to this space which is continuous. Though you are calling it path, but it's because 0 and 1 are mapped on the same point, you have a quotient topology which tells you that the same map will define a map from S1 unit circle to this. So basically you see unit circle as one whole, and intuition is that you are just checking what happens to copies of S1. And for example in S1 itself, so I have a map from I to S1. So okay, so my path could be like, you know, either it goes around once, okay, no matter what speed. You can go fast, slow, stop somewhere, have some cup of tea at this point and then again continue, okay. Take a break, you are tired, so you can go here, stop here for some time, then go, doesn't matter, okay. For some part of interval I, you stop there, or you stop finitely many times, it doesn't matter, okay. Or you go back, you go, if you are going this way, you go back, so like here, and then again you go back and then you go faster, it doesn't matter, because in between path I can break into parts, like you go this much, then this one is same as being here, and then you start here. So all these are same. Y you get Z. So if I went like this and came back, that's also a path, right? If I go little bit and come back, that's also a path, right? But that is same as the point, that a constant path. If I went up to here and came back, then that's same as this stopping here. It's just they are homotopic. But if I go once, there is no way that if you learn more homotopy fundamental group, there is no way that this going once is homotopic to a constant path. You will not get that, okay. So that is actually the generator. You go twice, it's the square of that, right, because you go once and second time, then it's double the speed. You are going first one and second, so that's going to be alpha times alpha, 3 times alpha. Inverse is opposite direction, like that, okay. So that's fundamental group geometrically is Z, because this one corresponds to one generator. So homotopy typically is a map from S1 to continuous map from S1 to the space, okay. But we want to say starts and ends at that point which we have fixed, so we say from I to that where endpoints are going, okay. So this is sort of a crash course on just introduction to fundamental group. We'll do covering spaces tomorrow, and I'll add more to I'll combine fundamental group and covering spaces, but you see this is a course for almost the whole semester, so I will only give some flavor and not anything more. Thank you very much. Whose is this? Sorry. So if I have two paths, let's say alpha and beta from x0 from I to x, so these are continuous maps, right, such that they have same beginning and end point. So let's say x0 to x1, this is my x, and I have one path alpha and another path beta. I put an arrow, means it starts at 0 from here and ends at 1 here. So alpha is path homotopic to beta, okay, which is with a dot path homotopy. If you have like homotopy, but it should be little extra. So now your I is original space x and x is y. So there exists a continuous function I cross I to x such that ft10 is alpha t1, ft11 is beta t1, and f0 t2 is x0, and f1 t2 is x1. Because I cross I is convex, I mean I is convex and I cross I is also convex, unless I put this extra thing, every path will be homotopic to a single constant path. So just talking homotopy for path is not enough, so you have to put this condition, and you can draw like this is your I cross I, right? So this is 0 0 1 0 1 1 0 1. So this is your I cross I, x is 0 y is 1, okay, and you have a space x and you have point x0 to x1. So this is alpha and this is beta in this order. So what you do, what it says is this one goes to alpha, right? This one goes to beta, and the whole this line goes to x1, just the point, and whole this line goes to x0, sorry. So let's, so this line segment should go to x0 and this one should go to x0. So this is a copy of this here, and these things are pinched to put to x0 and x1. So if I vary these things, typically I can show that these are all these in a different way going there. Of course it can be going here and coming back also. I mean, it could be just, this is a, you know, heuristic picture. So now the main point about the 2 paths, to say that they are homotopic, for the first condition is their beginning point should be same, their end point should be same. Then only you can define path homotopy, otherwise you cannot define, right? And the second thing is that again you can say that remark, so what you say is that during homotopy this beginning point and end point remain fixed, okay, and all these lines define paths from x0 to x1, right? Isn't it? Because this line goes to x0, this line goes to x1, and if I take a fixed line or even a curve here like this, its image is going to be, because you can, this f is continuous, so if you restrict, you get a continuous map to that, any of these lines or this, and you get a continuous path from x0 to x1. Path is continuous. Okay. Now similarly, as we said that homotopy is an equivalence relation, path homotopy is an equivalence relation. Relation between paths from x0 to x1. Okay, so of course their endpoints have to be fixed, otherwise I cannot define equivalence, the path homotopy. So for alpha you will say f t1 t2 is just alpha t1, that will give you alpha is homotopic to alpha. And if you have alpha is homotopic to beta and then you want to say beta is path homotopic to alpha, you just interchange ft1 t2. So gt1 t2 will be ft1 1 minus t2, that will give you. Now for three things you compress your f. So suppose you have f and g. So this is my I cross I expand this to, so this is I cross 0 half and I cross half 1, and I put f here and g here to get h. Okay, so combine. I'm not giving you more information because I need to do many things. So let me just now put so maybe I'll remove this, but before that I might want to say that just one little thing, that if I have f from x to y and continuous map, and if I have two parts alpha and beta from I to x, such that alpha is path homotopic to beta, so it's this homotopy with a dot is the notation for path homotopy. When you write this, it means that their beginning points are same for alpha beta and end points are same for alpha beta. Then you can show that f is composite alpha is path homotopic to f composite beta. Okay. Same way as you have homotopy between alpha and beta for x, you just compose it with f and you will get that. Okay. So let me now define what is called an inverse of alpha. So maybe I'll have to remove this. I'm not very good at using board very efficiently, but so this is quite easy for everybody to follow. So I am following the book Singer and Thorpe, and you will find most things there. So I'm only doing two, so few things. So given alpha from I to x, so this is like alpha like this, let's say from some beginning. So this is alpha 0, which is x0, and alpha 1, right? These points, these are in x, continuous. You can define alpha inverse from I to x, which is alpha inverse t equal to alpha 1 minus t, okay, for t in 0, 1. Now it's continuous because it is a composition of two maps, t going to 1 minus t, which is continuous from I to I and alpha. So this is continuous, and it will go from alpha 1 to alpha 0, right? And we will see why it's called inverse at some point, but it's just the direction is reversed, right? And the other thing is that if you have alpha 0 is path homotopic to alpha 1, so these are two maps starting at same beginning and end point with same fixed end points, then this is easy, because suppose you have a f from x cross I cross I. So this is the path homotopy between alpha 0 and alpha 1. For this one, suppose you want to say G from I cross I to x, you define G T1 T2 is f 1 minus T1. So now you can see that this would do the trick. 1 minus oh yeah, okay, sorry. No, this is correct, right? This is correct. So this one, let's say G T1 0, what do you get? F 1 minus T1 0, which is alpha 0 1 minus T1, which is alpha 0 inverse, and similar. Okay, so this is for the first part. Not for the second part, you do that is for the reversing alpha 0 alpha 1 alpha 1 alpha 0, but this is for the first. And similarly, if you put 1 here, you get 1 here, and then you get 1 here, and you get 1 here. Okay, so the interesting thing would be that if I combine alpha and, so you can combine two paths now. Let's say you have a path from x0 to x1 to x2 in x. So this is suppose alpha and this is beta. I want now, if you remember your path connected space things, you can combine two paths by going double the speed along alpha and then double the speed along beta. So alpha beta is defined from I to x as so alpha beta t equal to alpha 2t 0 less than t less than half. So this will go 0 to 1. So the alpha half is going to be x1, alpha 0 is going to be x0, and then this is beta 2t minus 1 half less than t less than. Okay. So this is, you're going double the speed and this double the speed, so you get this thing. Now if I have two paths like, let's say alpha 0 and alpha and beta 0 and beta, which are path homotopic. So if you have alpha 0 is path homotopic to alpha and beta 0 is path homotopic to beta, this implies alpha 0 beta 0 to alpha beta. You can also do other way. Alpha beta 0 is path homotopic to alpha 0 beta, or even alpha beta 0 path homotopic to alpha beta 0 beta, whatever, there are many things you can interchange. Okay, so you can combine two paths like this And so similarly you will be able to combine alpha and alpha inverse, because one starts from x0 to x1, other starts from x1 to x0. And we will see that when you combine alpha 0 and alpha inverse, you will get a constant homotopic to constant path at x0. So let ex0, let me just so here for these things you do, so if you have f here and g here, h will be like, you compress this way. So you have alpha 0, beta 0 here, 0 to half is alpha 0, half to 1, and alpha 1, alpha beta. And here suppose I have alpha 0 and alpha homotopy f and g, this will give you h. Okay, so this is 0 half, 1 half. Okay, so now you have an equivalence relation for paths, right? So you define this is an equivalence class. So let's say this is same as, so all paths from x0 to x1 which are homotopic to this. So let's say beta, such that alpha is path homotopic to beta, and of course when you say that, endpoint of alpha and endpoint of beta are same, means x0 to x1, both are from x0 to x1 for some x0 x1, right? So this is called equivalence path of alpha like this. So we know that they are it's an equivalence relation between paths between 2 points. So now you can also define combination of alpha beta as alpha beta. So it's starting from x0 to x1, x1 to x2, then you can do this. Okay, and you can also do okay. So this we already saw, and you can also, why this one is not so good. There's no other duster, no? It's very bad duster. And you can define alpha inverse equal to equivalence class of alpha inverse. So what you do is you take closed paths and then define. Means you start a path from a point and end at that same point. Okay. For example, in R2 you can just draw a loop, right? A path which is starting at point x0 and ending at point x0. So I should hurry up, my time is almost over. So alpha is a closed path I to x continuous such that alpha 0 equal to alpha 1 equal to, let us say, x0. Now you can see you get a group, because so what is fundamental group, which is denoted by pi 1 x x0 is equivalence classes of alpha such that, so these are paths which such that alpha 0 equal to alpha 1 equal to point x0. So these are continuous map from I to x such that two endpoints go to 0 and 1 go to the same point. Okay. Now this is a group. Why? Because we will take alpha alpha inverse, this is same as alpha alpha inverse is Ex0, and this is same as alpha inverse alpha as Ex0, because x0 and x1 are set. So you have inverse, you have associativity, right, and you have the group operation alpha beta, because all paths are starting from x0 to x0. Like you have alpha, here is x0, and you have, let us say, beta. So you go alpha, so this is your beta. So you go double the speed alpha and then you go double the speed beta, you can do alpha beta. It need not be abelian, but if alpha and beta commute, then it will be abelian, which happens in groups. If your base topological space is a group, then it happens. So now if your space is path connected, so suppose I have, so this defines what is called a fundamental group, and it uses this, so for example, for fundamental group of Rn will be trivial, because you can, because of convexity, you can find homotopy between the constant path at x0 and any path. So like if alpha, so let's just quickly do, if Rn, so if I have alpha, let's say path, so x0 belongs to Rn and alpha is a path from I to x such that alpha 0 equal to alpha 1 equal to x0 in Rn, and this is continuous, then you can define homotopy f T1 T2 is going to be alpha, what will you do? So let's say 1 minus T2 alpha T1 plus T2 Ex0. Okay. This just means that the point T2 is multiplied to x0, and that's your point. So now this is a continuous map homotopy. Now ft10 is alpha t1 and ft2 t11 is ex0, and you can see that if I put t1 as 0, then this is x0, so it's a combination of x0, convex combination, so you will get x0 and 1 also you can see. So any path, co-closed path in alpha is path homotopic to a constant path, then you get that pi 1 Rn x0 is trivial, is ex0. Sorry, okay, but this is independent of x0, right? I can start at any x0 and I'll get. Now, if you have a path connected space, you can show, so suppose I have a path, so I take paths at x0 and I have one other point x1, and I want to consider what happens if I take fundamental group here and here. So I can take, because it's path connected, I can take a path gamma and I can consider this as path gamma inverse alpha and then gamma, that becomes a path at x1. So this is a so given any path gamma, you get gamma hash from pi 1 x x0 to pi 1 x x1, which is just going to, so if I take any alpha, that maps to gamma inverse. So this map gamma is actually this way. So gamma inverse alpha gamma, and this gives, actually one can check, it's a group homomorphism and it's an isomorphism because it has an inverse also. Gamma hash inverse will become the inverse. So it's, so in a path connected space, fundamental group is uniquely defined at every point. It's the same, they are isomorphic. So you just say fundamental group of that space, that surface. Okay. So now I have to stop because we have 5 minutes over time, but let me see if, so if you have that they are okay. So if you have a map f from x to y, okay, there I can, then you can define a map f star from phi 1 x x to phi 1 y fx. So if you have a continuous map f from x to y continuous, then you can define f star from pi 1 x x0 to pi 1 y fx0 such that, so that is defined as f star alpha is f composite alpha. Okay, and this is a group homomorphism, you can see, and because alpha beta will go f star f composite alpha beta, which is actually, since alpha and beta are like double the speed and you are a composite, it will give you f composite alpha and f composite beta. So this is a group homomorphism. Okay, and you can show that if two surfaces are, two topological spaces are of same homotopy type, and of course they are all path connected, then their fundamental groups are isomorphic by using the maps f and g and so on, which will give you f star g star, and then you will get identity and stuff like that. So for example, S1, which I am not going into, but fundamental group of S1 is the group of integer Z, and then you saw that S1 cross I are 2 minus 0, they are all of same homotopy type, right, all of them. So they all have fundamental group S1, and so there are many surfaces, like if you take figure 8, fundamental group is going to be free group on 2 generator and it's non-abelian, and but if your base space is a topological group means it's a topological space but group operations are continuous, then fundamental group is always abelian. Okay, and we will tomorrow do covering space and connect fundamental group with covering space. So now you saw S1 as Z, but if I do S1 cross S1 m times, then it will be Z cross Z cross Z m times. You can show that, and so fundamental group just get multiplied. But S1 has one hole, right, in the sense, so the surfaces with one hole in Euclidean space, more or less you can show that they have same fundamental. But there is a long theory about this, but when he says surface with genus G, means it has sort of G G number of holes, okay. So I'll stop here, and if you have any questions you can ask me now or you can ask me later. Yeah, I think there are no questions on the YouTube, right? So maybe I should. Yeah. Yeah. Yes, because A, B and 0, 1 are homeomorphic, so you can change, you can replace 0, 1 with any interval A, B, but you just want to be consistent, so it's convenient to use I, because you see for path also, when you say path connected, you can use any interval A, B, but we use, I mean it's a continuous, there is a homeomorphism between I and A, B, yes. No, then what are the endpoints? So, yeah, anything is allowed. You can go alpha like this, and you can, so this is your alpha, you can go beta like this also. Continuous, it should be continuous. You can also do like alpha, this is also a path, right? All you need is continuity. The other thing is, actually when interval AB or 0, 1, when it's mapping, you are actually mapping your, so when you identify two endpoints, it's like it is a map from S1 to this space which is continuous. Though you are calling it path, but it's because 0 and 1 are mapped on the same point, you have a quotient topology which tells you that the same map will define a map from S1 unit circle to this. So basically you see unit circle as one hole, and intuition is that you are just checking what happens to copies of S1. And for example in S1 itself, so I have a map from I to S1. So okay, so my path could be like, you know, either it goes around once, okay, no matter what speed. You can go fast, slow, stop somewhere, have some cup of tea at this point and then again continue, okay. Take a break, you are tired, so you can go here, stop here for some time, then go, doesn't matter, okay. For some part of interval I, you stop there, or you stop finitely many times, it doesn't matter, okay. Or you go back, you go, if you are going this way, you go back, so like here, and then again you go back, and then you go faster, it doesn't matter, because in between path I can break into parts, like you go this much, then this one is same as being here, and then you start here. So all these are same. Why you get Z? So if I went like this and came back, that's also a path, right? If I go little bit and come back, that's also a path, right? But that is same as the point. that constant path. If I went up to here and came back, then that's same as this stopping here. It's just they are homotopic. But if I go once, there is no way that if you learn more homotopy fundamental group, there is no way that this going once is homotopic to a constant path. You will not get that. Okay. So that is actually the generator. You go twice, it's the square of that, right? Because you go once and second time, then it's double the speed. You're going first one and second. So that's going to be alpha times alpha, 3 times alpha. Inverse is opposite direction, like that. Okay. So that's fundamental group geometrically is Z, because this one corresponds to one generator. So homotopy typically is a map from S1 to continuous map from S1 to the space. Okay, but we want to say starts and ends at that point which we have fixed, so we say from I to that where endpoints are going. Okay, so this is sort of a crash course on just introduction to fundamental group. We'll do covering spaces tomorrow and I'll add more to. I'll combine fundamental group and covering spaces, but you see this is a course for almost the whole semester, so I will only give some flavor and not anything more. Thank you very much. Whose is this? Sorry.